Hello. Thanks for that. Excuse me. Gosh, yeah, I've got a bug in my throat. Can I use some of this water? First of all, I'd like to thank the organisers for inviting me. This is a wonderful group of people, I think. I enjoy the company. There's a lot of young people, which makes it a very vibrant thing. I think most of the young people are doing all the hard work. Yeah, and it's great to be part of this community. Although what I'm going to talk about is something that's quite not controversial, it's unconventional. And it's about time and the direction of entropy increase. What I mean here is that it's not the traditional way that we think about where the direction of time comes from, but I'm going to take you to I'm going to show you an argument where it's more fundamental than entropy increase. So the direction of time is not something that we get from entropy increases, which currently that's the conventional view, but from something deeper. So just to show you the kind of thing I'm thinking about, imagine that there's a tree, some wind is blowing, and leaves are falling on the ground. If you don't feel the wind and you see the pattern of leaves on the ground, that will you'll tell from that pattern the direction that the wind has been blowing. Okay? The leaves on the ground are just evidence of the direction. They don't cause the direction. And that's like entropy and the way that we see entropy. Entropy is just evidence of something. It doesn't cause the direction of time. What I'm talking about is actually the cause. Okay, so I published a paper on this in 2016 and it went viral. That's the reference. Read it, discussed it, and it got marked up by 5,000 votes, which is nice. It means a lot of people were attempting to understand it. So it's 50,000 downloads and so on. And New Scientist in 2017 included my theory of time as one of the 5 best theories of time. I don't know what they call the 5 best theories. I just think mine's the best anyway. So anyway, so it's got a bit of airplay. I was very nervous and sort of talking about this because it's so unconventional, but there is something seriously going on here that I think is worthwhile looking into. Okay, so I do want to talk about Lata Smits' paradox, and that's to do with the fact that our laws of physics are symmetric in time. So if you take this is a spatial plane, x and y, and time is in the vertical direction, and here's a container containing a gas, and there's a leak. Okay, so we know various properties about this, thermodynamic properties about the gas, but it's leaking. Now, if we use our laws of physics to predict what's going to happen in this direction of time, you would say that the particles leak out and the entropy is going to increase. Likewise, if you went in the opposite direction, you said, I want to see what happens down here, well, you would also predict that the entropy increases because the laws of physics are time symmetric. Now, we don't have information about the momentum and position of the particles. We only have this information, which are the macroscopic properties, and so that's why the entropy increases in both directions. And the symmetry here is due to the time-symmetric dynamical laws. Now, because of this, what we would say is that if you see entropy increasing, it means that there's evolution in that direction. Okay, that's what we mean by the direction of time. There's evolution in that direction. Okay, so evolution in that direction. Well, here is this increase in entropy is associated with evolution in this direction. And so that's what we mean by the direction of time. It's the direction of time evolution. Now, we have evidence that this is the same direction throughout space and time, so that it doesn't matter where you are on Earth or a distant galaxy, that this direction in time is the same, which is, well, it's kind of interesting that it would be the case. We associate it with causality as well. When you see a direction of entropy increase, you associate that with causality. So we have an arrow deciding the difference between cause and effect. But there should be a symmetry, because just like in the Lata Smits paradox, if we get an increase in one direction, there's nothing to say that, from this point here, there's an increase in the opposite direction. So where is the high entropy state in the past? And similarly with matter, we have abundance of matter at the moment. For symmetry, shouldn't there be antimatter somewhere as well? Now, we don't have a reference for time in the sense of the direction of time. The universe doesn't have one, an external reference, because it's just the universe. So we can't say, the universe can't select to go in one direction rather than the other. It must be symmetric. Okay, there's no way that universe could have decided. I mean, the universe doesn't decide anything, but there's just no mechanism for the universe to suddenly go off in one direction of time and not the other. There's nothing to support that at all. So these are anomalies: the entropy anomaly and the matter-antimatter anomaly. We call them arrows of time, but actually they're anomalies because these symmetries shouldn't exist. Now, recently there's been a couple of solutions proposed to these problems. Carroll and Chen resolved the entropy problem by postulating an entropy increase into the past before the Big Bang. Barber used chaos theory and gravity, Newtonian gravity, to do the same. Not to do with the Big Bang, but in terms of a symmetric arrow. And recently, Turok and others have used the CPT theorem, so have a CPT symmetric. This thing has run out of batteries power. Now, those resolutions leave out one thing. There's another anomaly, and that's the T-violation anomaly, which is what I want to talk about. So the T-violation anomaly is associated with the discrete symmetries. Well, there's CP and T discrete symmetries: charge conjugation, parity inversion, and time reversal. And so these violations of these symmetries were discovered, well, first of all in 1956 and then in 1964. And for the T violation, that's in just a few years ago in 2012. The idea is that, well, just because the T violation is important, I'll take you through the evidence of that just briefly. So the idea is that you have this is at the Stanford SLAC particle accelerator. You have a beam of particles coming along, and you produce B mesons. And there's a whole variety of things that come out, and they decay in different ways. But what you do is you select sub-ensembles and look for this particular thing, that you get a B bar, which is an anti-meson, changing into later a B minus. Okay, you don't need to know what these things are, but it's just going from a B bar to a B minus. And then different experiments, different events, it's the same equipment, but different events, where you get a B minus changing into a B bar. Now, the time taken for those processes is found to be different. Okay, and that's a direct violation of T invariance, that they're different. The idea is that, so the process from B bar to B minus is governed by a Hamiltonian. Now, to go in the reverse direction, so going from the B minus to B bar, it's equivalent to the time reversal version of the Hamiltonian. And because it's a different time, we know this Hamiltonian is going to be different from the untransformed one. So very briefly, I'm leaving out a lot of details here, but The B and B bar are particle and antiparticle. If you look at the Hamiltonian of those terms, these off-diagonal, so they rotate into each other, that if you look at the off-diagonal elements, they're complex, and the time inverted version is different. Okay, so it's just a simple thing like that, just complex elements that under the time reversal operation change phase. Now, that means that there are two Hamiltonians. People don't talk about this T violation is recognised, but it's associated with two Hamiltonians. One Hamiltonian for one direction of time, another one for the other direction. Now that's bizarre. I think it's absolutely bizarre. The T violation, just in the way that people talk about it, is bizarre enough. But when you think about that there are two Hamiltonians, and all our theories just incorporate one version of the Hamiltonian, then maybe there is a connection here to do with time. Okay? There's something deep with time. It's not like entropy increase was just evidence of something going through, but something really dynamic here. Well, our theories only include one version of the Hamiltonian, and to be symmetric, time symmetric, they should include both. And this is what I call the T violation anomaly. And the solution to this anomaly is the quantum theory of time. The anomaly is described in this chapter in a book if you want to read about it some more. So the quantum theory of time is based upon this idea is that, am I doing all right for time? So what we want to do is something more fundamental than just an entropy increase. What we want to do is actually try and discover if there's a connection between this T violation and dynamics. Is there something driving the universe through time? So in order to do that, you realize that time and space are different. At the relativistic level, they're interconvertible. Okay, so they're of the same kind of thing. But when it comes to dynamics, space and time are treated very differently. So there's a background, a space-time background where time and space are of the same kind of material, the same kind of thing, because they're interconvertible. But on top of that background, there is the dynamics, which treats time and space differently. Because the dynamics is about translations over time and not about translations over space. I mean, you can translate over space as you move over time, but the dynamics is that there's this continuous translation over time. And conservation laws are symmetries of that dynamics, and they apply to time and very differently to the way they apply to space. In fact, they say nothing about space. They say that if an object, if mass is conserved, then you see that mass all the way along time. It doesn't say anything, restrict anything about its position in space. So these, the dynamics and the conservation laws treat time and space very differently. Maybe they're not fundamental. Maybe the dynamics isn't fundamental. Maybe the background is fundamental, but these dynamics are not. If we ignore conservation laws and dynamics, we can do funny things. Like in quantum mechanics, we can have a particle that is localized in space. Whoa. Localized in space, but normally, conventionally, you can't localize it over time. Okay, so, but that's because we've got conservation laws. If we do away with conservation laws, then we can do this. In other words, we can represent particles as if they are virtual particles. A virtual particle comes into existence and disappears, and that's what I'm talking about here. So you don't have mass is no longer conserved. It would come into existence and disappear. So if we throw away dynamics and conservation laws, then we can represent objects on the space-time background in a symmetric way. And then the idea is to use phenomenological details, like to do with T violation, to get the sorts of things that we're familiar with. Okay, so we start off with this. There's mass is not conserved, no dynamics. Things look like virtual particles, and then we get something that becomes continuous and conservation laws apply. This idea isn't new. I mean, the idea of using T violation is new, but the idea of taking a virtual particle and translating it along time and making it a real particle is actually quite old. Feynman looks at it, Schwinger as well, and a number of people. They're called parameterized theories, fully relativistically invariant, and it's this idea of parameterizing local things that are localized in time. So there is a connection with some serious work. Now, so in order to go from this situation where we don't have conservation laws and no dynamics to this one, we need to look at something that's phenomenological. Okay, well, if we're thinking about moving through time, so displacements in time, and the generators of displacement or translations over time is given by the Hamiltonian. It's the Hamiltonian that generates these translations. And the momentum operator generates translations in space. So here we have two generators. Now, the thing is, these generators are quite different when it comes to the discrete symmetries. The Hamiltonian violates the discrete symmetries, and the momentum operator is quite inert when it comes to the discrete symmetries. Okay, so here we have phenomenology that has enough difference between space and time to give us this kind of thing that we want. Okay, so what we have is a generation of translations in time. You have a different one for the two directions, whereas for translations in space, we use the same operator. So there's a difference in these things between time and space. So the idea then is to make use of this to build up a theory where dynamics emerges. And I use 4 principles. The first principle, just very briefly, is that states have the same construction in space and time. So we have them particles appearing as virtual particles. The time evolution is directional. So this is brand new, that there's one version of the Hamiltonian for forwards and another version for the backwards direction. Now, that means because there are two Hamiltonians, conventionally we have one Hamiltonian and we have two time evolution operators, forwards and backwards. If you have two Hamiltonians, you then have 4 operators. Okay, so we need some way to work out what these operators mean. So here are the unitary evolution operators. Well, the idea is that the forwards, this Hamiltonian here with F on it, generates time evolution in a direction, and that's associated with causality in that direction. And then there's the time reversed version of that Hamiltonian for generating translations the opposite. Now, if you just take the mathematical inverses of those, you get 2 other operators, and that's just rewinding. So just like if we think about conventionally that you have a direction of causality, so causes precede effects, but you can wind back that evolution just by going backwards, and that's unwinding the causal evolution. Okay, so that's what these operators do, is just unwind. So, I mean, there are these 4 operators. I'm not making this up. There are 4, and we need a way to interpret it, and I'm suggesting that this is the way we should interpret it. Okay, so another principle is that there's a fundamental resolution limit in space and time. You could take these as at the Planck scale, and that a state is represented by a quantum path, like a quantum walk, but it's a little different. It's actually a virtual walk rather than a real walk. So here we have, this is in space. We want to represent a particle at the origin here, and we represent it as a quantum walk, so superposition of random walks. And you know that a superposition of random walks, or even just random walks, will have a Gaussian distribution. Okay, so there's no interference here when you take this superposition of random walks. You end up with a Gaussian. The same thing happens in time when you have T-symmetry. T-symmetry is the absence of T-violation. So if the 2 Hamiltonians are the same thing, okay, so they respect time reversal symmetry, then it's exactly the same for space. So we can have these virtual walks in time and build up a Gaussian distribution in time. okay, just from these walks, random walks. There's no dynamics because it's just like a virtual particle, so that you can represent a particle in space and time as being localized at a point in space and time. Now, if you just turn on T-violation, and the way that T-violation appears in the theory is that you get interference from different paths, and the amount of interference is associated with the commutator of the two versions of the Hamiltonian. In fact, we only need the expectation value of the commutator. So when this is non-zero, you get interference between these paths, just like you find in quantum walks, you get lots of interference, and it breaks up into two Gaussians. And, well, there's details I can't go into, but you end up with a series of these things that get further and further apart. So it's a superposition of two Gaussians which are further and further apart. And what that effectively does is move the virtual particle over time. And you find that if you ask the question, will I find this particle at a particular time? Well, there's a set of these things, and there will be a representation of the particle there. In other words, the mass will be conserved. Doesn't matter what time you ask, any time, this is a divergent sequence, at any time you'll find a representation of the particle at that time. And the way that this sequence of states changes from one term to the next is governed by the Schrödinger equation. That just is, well, it's just the way that it happens. Whoops. And so by overlapping these, effectively overlapping the virtual particles, I mean, it's a representation of a virtual particle at different points in time, you end up with a continuous curve. In other words, you end up with a world line. You end up with a world line, okay? And so mass is conserved, and we have dynamical equations of motion. And if there was a reason, I mean, it's not included in the theory, I'm not as sophisticated as that, but if there was a reason to go from a radiation-dominated universe at t equals 0 and to a matter-dominated universe over here, because of T-symmetry, you would end up with an antimatter-dominated one over here. So we end up with this symmetric, time-symmetric theory. Okay. One of the things is that it's possible, well, there are potential experiments to do to test this, and one is that the peak of those Gaussians, that is the location in time where you expect this virtual particle, depends on, well, this is running out of power, but there's a lambda up in the top right-hand corner. There's the time, the peak time, it's inversely related to lambda, and lambda is associated with the commutator of the Hamiltonian, the two versions of the Hamiltonian. So what that means is that lambda parameter will change depending on how much T violation there is. And near a nuclear reactor, power reactor, there's a lot of neutrinos, antineutrinos being produced, in fact, megawatts. And neutrinos are thought to violate CP invariance, and as a result, they will violate T invariance. So this means that there will be more T violation close to the reactor core than elsewhere, and that should change the time registered on clocks. So I call this clock dysynchronization. It's a little bit like time dilation, but this is quantum in nature, associated with proximity to things like nuclear reactors, or just the local variation in T violation. Now to come to finally the thermodynamics question. So we know about fluctuation theorems, and so the Evans Seals fluctuation theorem goes something like this, is that you localize, so here we have phase space, P and Q, the plane here, the vertical planes are P and Q, that's phase space, and time is in the horizontal direction. So if you look at a system and you localize the state to some region of this phase space, over time you'll find that there are a whole series of trajectories that map out from that original area on phase space. Okay, so the capital gamma represents these a bundle of trajectories. Because there is time symmetry in, I mean, we're just using classical physics for this, there is these things are time symmetric, these trajectories are time symmetric, we can start at a final, well, the time reversed state, so delta V, that region of phase space. If we look at delta V asterisk at the later time, you can follow those points or trajectories going backwards in time and come to the present. And the fluctuation theorem is about the probability for following in the forwards direction, going from here, the probability that you get these trajectories compared to the probability that this would happen. Okay, and as everyone knows, that you get this exponential ratio. In other words, that it's highly probable that the entropy will increase in that direction from this. Okay, that now a way to look at this, in fact, if you look at the derivation, you find that there's a heat flow out of the system because of this, the density in phase space is increasing. So let's just call it an energy outflow. Whereas when you do the time reverse, what you see is that there will be an energy inflow. Okay, for this to be contracted in phase space, there must be work done on the system. And here that you can take either heat out or the system can do work on its environment. Okay, we could reverse this because everything is time symmetric. We could just start over here on the right of the screen and look at it in the opposite sense and just relabel things and say that the lower set of trajectories is the one that we want and the upper ones are the time reversed ones. Okay, and if you do that, everything is it's just a question of relabeling. You'll also find that there's an exponential, the reverse fluctuations are exponentially damped. In other words, it predicts that there's a high probability of entropy increase in this direction. I mean, it's completely symmetric. It's just relabeling. So the fluctuation theorem doesn't actually tell you anything about the direction of time. And this is just Lata Smits paradox again. Okay, can't tell you anything. All it can do is generalize the second law. And the second law itself, because we know of Lata Smits paradox, doesn't tell us anything specifically about this, the direction of time because of these time symmetric physical laws. But there is a difference now. So what we're talking about here is that this branch of the evolution is associated with the unitary operator, unitary evolution operator, associated with the forwards Hamiltonian. So there's something that's causal that's happening in that direction. So it's dominated by this Hamiltonian, and so that there is no way to interpret this in the opposite direction. Okay, it's just not a matter of saying, well, this is the, I can look at this from going in the opposite direction. So really there's a causal direction associated with the way that this virtual particle is translated over time. In fact, there's an ordering here, so it's an ordered set. Okay, so looking at the ordered set in a different order is a dramatically different thing. It's not simply a relabeling. So in other words, it's this diagram, if we're talking about that part of the evolution, that is about energy outflow out of the system, and it's not simply something that you can easily just, a question of saying that things are going in a different time. In other words, we have a theory which talks about why the wind blows, in other words. Okay, it's not about just looking at the leaves on the ground, looking at patterns, but why something dynamic has actually happened. So I'm proposing this as a resolution to Lata Smits paradox. So just a brief overview of what I talked about is incorporating T-violation and resolving this anomaly, because there are two Hamiltonians and they need to be treated and dealt with, and 4 time evolution operators that need to be categorized and understood what they mean. And you end up with a theory that is experimentally testable, and at least I think it's a way of resolving Lata Smits' paradox. Thank you.
So I'm slightly puzzled by 2 things. The first